Okay, as long as we've talked about linear dependence, let's talk about linear independence. So this is the same motivating example. In R2, what if you just had these two vectors? What if you had the span of 1, 1 and 1, negative 1? Is it still the case that they're linearly dependent? And what if not? Well, a subset S of a vector space V that is not linearly dependent is called linearly independent. That might seem obvious, but that's what we're working with. So how could you say that this subset was linearly independent? Well, remember, to say that it was linearly dependent, you had to say that there was an A1 and an A2, not both 0, that would make this equation true. So how can that not be the case if the only way to make this true is A1 equals 0 and A2 equals 0? Then it is linearly independent. So on the left we have A1 times 1 plus 0 and plus A2, I misspoke, and then in the right component I have A1 minus A2 equals 0, 0. So let's look at that system of equations. A1 plus A2 equals 0, A1 minus A2 equals 0. If you add those two lines, you get 2A1 equals 0, or A1 equals 0 in the reals. And if you subtract those two lines, this minus that, you get A1 minus A1, A2 minus negative A2, so you get 2A2 equals 0, or A2 equals 0. So both of those together mean that this set is linearly independent. In other words, somehow this is the most efficient way that this span can be built. There's nothing that can be dropped. So we are going to look at a different example. Let's look at degree 2 and less polynomials, and let's see if we can convince ourselves that those three vectors are linearly independent. So let's choose A, B, and C real numbers such that A times 2x plus 1 plus B times x squared plus x plus C times x squared plus 2 equals 0. That's the 0 polynomial. So let's expand all of this out. Where do my quadratic terms come from? I get B plus C x squared, right? Where do my linear terms come from? I guess I have 2ax here, b many x's here. And where do my constant terms come from? I have a there, I have no constant terms there, and I have 2c. And that all equals 0. Or if you really want to emphasize, 0x squared plus 0x plus 0. And so you have a system of three equations. So b plus c equals 0, 2a plus b equals 0, and a plus 2c equals 0. So we're looking sort of for the easiest variable to eliminate. It looks like we might be able to eliminate b from the first two if we just subtract. So if you subtract the second equation from the first equation, we get, let's see, c minus 2a equals 0. And I've got, if I put it in the other order, actually I probably should put it in the other order to begin with. So I have it in alphabetical order. Negative 2a plus c equals 0, and a plus 2c equals 0. And so then I will scale this second one. I'll multiply it times 2. So I get 2a plus 4c equals 0, and negative 2a plus c equals 0. And so that's 5c equals 0, or c equals 0, right? Fairly straightforward now to put it into this equation. So b plus 0 equals 0. So b equals 0, right? And let's see, a plus 2 times 0 equals 0. So a equals 0. Therefore, a equals b equals c equals 0, and the set is linearly independent. That's a little sloppy, but hopefully you can read it. The set's linearly independent. Now, there are some key facts that I want to talk to you about. The empty set is linearly independent. Think about the definition here. If you think about the definition, well, it does not satisfy the definition of linearly dependent because you can't pick any vectors there, so it's linearly independent. Now, if you have a set containing a single vector, as long as it's non-zero, it's linearly independent. Think about that. If you have any vector times u, if u is non-zero, the only way that can be equal to 0 is if the scalar is 0. And finally, think about the negated definition of linearly dependent. Okay, this is significant, probably the most significant thing on here, because in fact, we don't usually use the fact that linearly independent is just not linearly dependent. We usually negate the definition. So a set S is linearly independent. Now think about that definition. In fact, maybe I'll even bring it up here. There was our definition of independent. If and only if there does not exist a set of vectors and a set of not all zero vectors so that this happens. In other words, if and only if the only linear system U1 to UN and A1 to AN in F is the only linear system A1U1 plus AN UN equals 0 is the one where A1 equals A2 equals AN equals 0, or S equals the empty set. So I should recognize another way to negate this statement is there aren't vectors like that, right? So this is really handy if you want to show something is linearly independent. Pick a system like we did above and force those coefficients to be 0. Show that they must be 0.